The theme in exercise 1820 is the power of halogens. In all of these, A, B, C, D, and all of these for 1820, you're doing reactions, you're changing things, and in each case, you're able to make the change because of adding a halogen onto the molecule by doing radical halogenation with N-bromosuccinimide. Okay, ignoring that introduction, let's say you came face to face with this problem. How do you analyze it? The first thing you want to check for is if the number of carbons change. There aren't too many ways, there aren't too many reactions you can use to add carbons or to take carbons away. And so if the number of carbons do change, then that narrows down what you need to build your synthesis around. In the molecule on the left, we have 6 carbons in the benzene ring, and in the molecule on the right, we also have 6 carbons in the benzene ring. So that doesn't change. In the molecule on the left, outside of the benzene ring, we have 1, 2, 3 carbons. And in the molecule on the right, outside of the benzene ring, we have 1, 2, 3 carbons. So both of these molecules have the same number of carbons. So we won't have to do anything special in terms of making new carbon-to-carbon bonds or breaking carbon-to-carbon bonds. What we do see here, though, is that a new thing is attached on the right, the OH. It wasn't there on the left, it is there on the right. So somehow we need to get that onto the molecule. Now, the window for putting things onto a molecule, the door that sort of opens up a whole bunch of possibilities to you, are the halogens. What we would like to do is to put a halogen on this molecule. Once you have a halogen on a molecule, then you can replace it with other stuff. In other words, you can substitute it with something else. For example, an OH by doing a substitution reaction, or you can eliminate it and leave a pi bond that you didn't have before. You can do elimination reactions. It leaves a whole bunch of possibilities open. And a really useful thing you want to know for putting a halogen on these molecules is to use radicals. A radical is a molecule that has an unpaired electron on it. It's really, really reactive. It reacts with the first thing it comes across, irrespective of how stable that thing is. Now, if you try to create a radical on this molecule, you'll create the radical at the weakest point of the molecule, or I should say, at the most reactive point of the molecule. The most reactive point on this molecule is the benzylic carbon, the carbon that's immediately bonded to the benzene ring. It's really stable because if you have really high energy intermediates, things like a carbocation, or a lone pair with a negative charge, or a radical, an electron that's unpaired, if you have those at that position, those are all going to be allylic to this pi bond. All of those species would exist in a p orbital, and that p orbital would be parallel to the p orbitals that are forming the pi bonds all throughout that ring. So that if you had a positive charge or a lone pair with a negative charge, those could spread out through these parallel p orbitals and delocalize over the ring. That would make them more stable. So that benzylic position is really reactive. And so when we treat it, when we react it with the recipe that creates that adds bromines on there through a radical reaction, the bromines will add to that benzylic position. So the recipe is use N-bromosuccinimide and heat. You could also use light, in which case they would write H nu instead of heat. So what's happening there? How does that happen? If you have N-bromosuccinimide, the way what that looks like is this molecule here. Oops. And this, if you heat it up, this bond between the nitrogen and the bromine is able to form a very reactive intermediate. It's able to form radicals. The electrons in that bond, there are 2. One of them can go onto the bromine, the other can go onto the nitrogen. That's homolytic cleavage. You're cleaving that bond in the same way on both sides, one electron to each side, and you end up with, after that homolytic cleavage, you end up with a radical on the nitrogen and a radical on the bromine. Now that bromine already had 3 lone pairs. So you end up with 2 radicals, 2 really reactive species. Now if you treat that with the benzene ring, the radical is able to, let me move this. The radical is able to steal a hydrogen from the benzene ring. So, from the benzylic position, I'm sorry. So, it's able to steal hydrogen, and the most vulnerable hydrogen is the hydrogen on the benzylic position. This is relatively stabilized, notice, because this radical, which is very unstable, that radical is being spread out through resonance. It's allylic to that top carbonyl, it's allylic to the bottom carbonyl, and notice how both of the carbonyls are conjugated with the pi bond, so that the negative charge is really spread out over the whole ring, which helps to stabilize it. So that molecule goes off and lives its own stable life. The bromine, on the other hand, swoops in and is able to steal one of the hydrogens. It donates its electron, it steals one of the electrons from the hydrogen. So you end up forming HBr. But notice this bond had 2 electrons in it. We've only showed where one went. The other one goes onto the benzylic position, so that you have a radical here now, and that's able to form because it's allylic to the pi bonds in the ring. So it's being stabilized by being spread out through those pi bonds. Well, when we first did our radical, when we turned N-bromo-6-cinnamide into a bromine radical, that didn't just happen to one molecule, that happened to trillions of N-bromo-6-cinnamides, and so another one of the bromine radicals that's formed can pair up with this new carbon radical, and it can form a new carbon, or it can form a new bond, a new sigma bond. So you end up with a bromine on the benzylic position. So long story short, if you treat a molecule that has a benzylic position with N-bromo-6-cinnamide, NBS, and heat, you end up getting that same molecule just with a bromine on the benzylic position. So that's nice, fun, interesting, but who cares? What can you do with a bromine? We didn't want a bromine, we wanted an alcohol. We wanted an OH. Bromine is not OH. But the reason why it's so valuable to put a bromine onto a molecule is because it opens up the possibility for substitution and elimination reactions. We just want to substitute the bromine for an OH, so we want to do a substitution reaction. Now it is a little crowded here, so we probably won't do an SN2 reaction. And also, the bromine can very easily leave. It can pick up its electrons and pop off, and leave as a bromide ion. It'll stabilize that negative charge with its huge volume. Bromine is even bigger than a chlorine, and a chlorine is as big as a methyl group, so it'll be able to stabilize itself that way. That would leave this carbocation behind, and then you can use that carbocation to do an SN1 reaction or an E1 reaction. So we want to think in terms of SN1 or E1 unless this is a primary carbon. If we had a different molecule, it was a primary carbon, it wouldn't be bulky, we could probably do an SN2 or an E2, but because it's kind of bulky there, we'll be thinking in terms of SN1. So we want to replace the bromine with an OH, but not with an SN2 reaction, so we don't want to use a strong nucleophile. If you tried to use a strong nucleophile, like sodium hydroxide, and remember, the sodium here is just a counter ion, the nucleophile is the hydroxide. This may do the substitution reaction, but it may try to steal one of the hydrogens instead. They're more vulnerable. The electrons would go over, you'd kick the bromine off, and you'd end up with a pi bond. You'd do an elimination reaction instead. So it's risky to treat that with a strong base or a strong nucleophile, because you'll end up getting messy products. So instead, treat it with a really weak oxygen nucleophile. And the poster child for that is water. Water is very stable by itself. It doesn't need to react. It's got its own thing going on. So you can treat it with that. That's not going to steal any of these beta hydrogens and make an elimination reaction happen. Instead, it'll sit by and bide its time. And when the bromine pops off to give you that carbocation, the water will be there waiting. And this nucleophilic oxygen with a slightly negative charge will attack the positive charge on the carbocation. So you'd end up with this. And all that needs is to lose one of its hydrogens to be a little bit more stable, and another water knocking into it hard enough is able to get that done. So that steals that hydrogen, this goes onto the oxygen there, and you are left with you're left with what you wanted, your original molecule there. So, the explanation for this one took a little long. You'll see that the next few will be much faster, but that's because I wanted to walk you through exactly how this NBS and heat reaction works, because it ends up being a really significant reaction. It allows you to place a halogen on the molecule at the benzylic position, and that opens the door to elimination and substitution reactions. In this case, it was an SN1 reaction because this was really bulky. It was kind of a crowded area, and if you have an SN1 reaction, you form the carbocation intermediate, which in this case would be really stable because it's allylic to the ring, the pi bonds in the ring. And we just used a weak nucleophile here, because if we used something that's strong, it could have acted as a base and stolen the hydrogen and given us a double bond, which is not what we wanted. So that's what we have there. You can see how that's a similar thing would happen here. Now that we've sort of trained our eyes to see it, you look at this molecule, this ethylbenzene, and immediately you're like, okay, benzylic position, that's what I'm going for. I know I can put something on there. And then second, you look at the product and you'd say, well, the number of carbons isn't different, but what is different is I have a double bond. How do you make a double bond? Elimination reactions. But to do an elimination reaction, you need a leaving group. No problem. NBS and heat. That'll put bromine on the benzylic position. Benzylic position, which is that atom, the carbon immediately bonded to the benzene. And it forms there because the radical intermediate is stabilized through resonance. And then you just do an elimination. So before we were worried about adding a base, because then it would cause an elimination. Here you want to do an elimination. And there are a couple bases that you would want to remember. There is sodium ethoxide, and there's also potassium terpetoxide. So this ET is referring to an ethyl group, so 1, 2 carbons, and then 2 carbons, and then you'd have the O. The oxygen there this is an ionic bond, so the oxygen is the more electronegative atom. It'll have a negative charge, and the sodium is just a positive charge. So that's sodium ethoxide, and it's a strong base. And this one is potassium terpetoxide. The TBU is referring to the fact that you have a tert-butyl group that's bonded to an oxygen. Here we have another ionic bond between a nonmetal, the oxygen, which takes the electrons, and the metal, which loses the electrons. And so either of these would function as good bases here. I personally would tend to gravitate toward the potassium terpetoxide just because it's so bulky. The tail of that is so bulky that it really prevents this from ever acting as a nucleophile. It very rarely acts as a nucleophile. It's almost always a base. In the case of sodium methoxide, it usually acts as a base, but it's also skinny enough where it can act as a nucleophile and cause substitution reactions. So either one would work. It'd be fine. It'd be acceptable. But I would tend to go for the potassium terpetoxide. So if you have that here, here's the terpetoxide. What that can do is it can steal the low-hanging fruit. That's the hydrogens that are open, exposed to the wind. It can steal that hydrogen, the electrons can go away toward the leaving group and kick the leaving group off. So you have proton transfer and loss of a leaving group, the signatures of an elimination reaction. And in that case, you would end up with the product you want. You end up getting styrene. So again, we used NBS in heat, N-bromosuccinimide in heat, to put bromine on the benzylic position, and then we used a base just to make an elimination reaction happen. So notice how that NBS in heat, adding that halogen, is a window to substitution reactions, like we saw in A, and to elimination reactions, like we saw in B. I'm going to minimize these, just so they don't get in the way of our next thing, which is this. Now here, you've formed a new carbon-to-carbon bond. But if we use our thinking, the same sort of process of thinking that we've been using, you have the benzylic position that's really reactive. And even if you didn't even look at the product, at this point you should be thinking, well, if all else fails, I'll add N-bromosuccinimide and heat. At least that will put a halogen on the benzylic position, and that opens the door for me to substitution and elimination reactions. Now here I have a bromine, but I don't want a bromine. I want a carbon triple bonded to a nitrogen. If only there were a way I could substitute a carbon triple bonded to a nitrogen for the bromine. But I've given myself away. Substitute, we'll do a substitution reaction. And this carbon here is a primary carbon. So an SN2 reaction is really possible here. In other words, we can just treat it with a strong nucleophile. We can take that piece, it's a carbon triple bonded to a nitrogen, right? Because we already have this one carbon here, so that's one. So we just need the other one, and then the nitrogen. And notice that you want the carbon to be the nucleophile, because it's the carbon that's going to be attacking that electrophilic center. Notice that it is electrophilic because the bromine is slightly electronegative and steals electron density from that carbon. You want this carbon here to attack that, right? That carbon to attach to carbon number 1. So you make that the nucleophile. It needs 2 more electrons anyway. That gives it a full negative charge. And that's a cyanide ion. You might have heard of the poison hydrogen cyanide. That's just this bonded to a hydrogen. So cyanide. You can use that as your nucleophile. That's going to attack the electrophilic carbon here and kick off this bromine. So an SN2 reaction, classic. And so what you get is that same carbon there, but now we have it attached to the carbon triple bonded to the nitrogen, which is exactly what we wanted. So this is the same thing as this. All right, last one. Oh, it looks scary. You've got rings now, extra rings. But notice it's really the same thing. You look at the benzene ring and you say, benzylic position, the carbon attached to the benzene ring, that's the reactive one, because that's where you can have really high energy intermediates that are stabilized through resonance with the ring. Well, even if all else fails, if you look at that, the molecule on the right is really the same. The only difference is, as the molecule on the left, the only difference is it has this weird methoxy group there. That it's an ether, right? You've created an ether, and ethers are usually named as branches. You have one carbon, so meth, and then an oxygen, so it's a methoxy group. Well, we don't know how to put a methoxy group on the benzylic position. What we do know is how to put a bromine on the benzylic position. You use N-bromosuccinimide and heat. Getting good at that. So you add that bromine there, and even if it's not what you wanted, you feel pretty satisfied. Well, the satisfaction wears off because that, unfortunately, is not really that close to our product. Although, wait a second, we have a bromine, but I really want a methoxy group. If only there was a way I could substitute the methoxy for the bromine. Wait a second, substitute. It's a substitution reaction that we need to do here. So a substitution reaction. Now this is a really crowded carbon. Like it's a tertiary carbon, you've got a big fat bromine there, you have rings around. No way, no how are you going to do an SN2 reaction there. So you're not going to come storming in with guns blazing with a little methoxy group. Like a methoxy group may be bonded to a metal, like sodium methoxide, and that's like, all right guys, clear out, I'm going to attack here. No way. It's too crowded. It'll get pushed away before it gets anywhere near that slightly positive carbon. Slightly positive because it's in the bond with the bromine, which is slightly negative. It's pulling the electrons to itself. So SN2 is not going to fly. What you can do in this scenario is an SN1 reaction. And in that case, you'd want to treat it with a more stable nucleophile, a weaker nucleophile. After all, if you treated it, if you actually mixed in a methoxide here, this is just going to end up stealing a beta hydrogen, and the electrons would go here and kick that off, and you'd be doing an elimination reaction. That has its time and place, but it's not here. So you don't want to do an elimination reaction, you want to avoid that, so that strong nucleophile is just going to be unhelpful. You can keep a similar thinking though. You can have the methoxy, but you can stabilize it by having the hydrogen on it. So methanol instead of methoxide. Methanol. And what that allows is for the leaving group, the bromine, to just pop off. First step of an SN1 reaction. If that pops off, and then you'd have the bromine, of course, flying around in solution, but it's able to stabilize the negative charge through its enormous girth. It just spreads it out, smears it out in three-dimensional space because it's so enormous and stabilizes it. Once it leaves, that leaves that carbon there as a carbocation. And now, because it has a full positive charge, the nucleophile, even though it's really weak, even this weak, stable nucleophile will attack it. So you have nucleophilic attack, second step for this substitution reaction. And that almost gives you your product. Oops. You just need another, like a water molecule, or even another methanol molecule to come on by and help a brother out and steal that hydrogen there. Those electrons go there. And that happens because this oxygen is slightly negative and it's bouncing around, knocking around, it's got its own energy. It hits it hard enough and it just steals it. That's an equilibrium reaction. It'll get it back, but for a little while it'll steal it. And when it does, you end up with your beautiful product. Exactly what you want. So, in terms of the synthesis, if you were going to write the steps out, you'd have 1, NBS and heat. That puts the bromine on the benzylic position. 2, treat it with methanol. The Me here is just a methyl group, so that's like that. Treat it with methanol, and really you could just treat it with excess methanol, and that would give you your product, because the second equivalent of methanol will stabilize it by stealing that hydrogen there. So really the lesson, the takeaway from this exercise, from exercise 1820, is that N-bromosuccinimide in heat gets things going. It opens up substitution and elimination, as we've seen in these exercises. And it does that by adding